Before starting, I just want to introduce you to new people coming to IFISC. One is Professor Lisa Angelutta, coming from the University of Oslo. We'll be here for 2 months working with problems of condensed matter and quantum turbulence with Cristobal and myself. And also Eduardo Colombo, who's a postdoc coming from Rio de Janeiro. We'll be here for 1 year working with theoretical ecology topics, including mobility and different things on interaction between ecological individuals. So welcome.
Okay, welcome to the colloquium for molecular changes. Today we have with us Christian Beck, who is a professor of applied mathematics in the School of Mathematical Sciences at Queen Mary University of London. There he leads the Dynamical Systems and Statistical Physics group, and he has been for the last 20 years. Before that, he got his degree in Aachen, in Germany, where he's from actually, and then he held several positions in Maryland, in the US, in Budapest, in Oslo, also in Warwick, looking how this permanent position in London. His current interests are varied. You'll see that he's worked on many things, but they basically spin around nonlinear dynamics, stochastic processes, and statistical physics, all topics which fit very well within his spirit. Be more specific, his work includes the mathematical modeling of complex systems and interdisciplinary applications with real-world complex systems like electricity network, which is something today, floodings, and many other things. Just to mention the variety of topics he's worked on, I'll mention that he's also interested in Josephson junctions and axionic dark matter, the cosmological constant, and other models of dark energy. So I would say that it's useful to have somebody whose interest is so broad. He's also a founding director of the Master in Mathematical. I mentioned that because, we're colleagues. That's very important to do. He's a Master in Mathematical Finance, and he teaches the postgraduate course Portfolio Theory and Risk Management. So sometime you give us a seminar on that, how to have our portfolios. Among his main duties, I will just mention a few, he's an editor of Europhysics Letters, Physica A, and Chaos, Solids and Fractals, journals where most of us have published or tried to publish papers in the past. I have known his scientific work for many years, but recently I had the chance to appreciate his kindness and well-being as the chair of the Statistical and Nonlinear Physics Division of the European Physical Society. If you're not a member of the European Physical Society, you should really consider joining the society. Okay, it's doing very good things, it's promoting the science, and I think we can also benefit by having a large community. That's our advertising part. I'll just mention, of course, he has published many papers, and has both without saying. I'd like to mention 2 books, which are also very different in topic. One is about thermodynamics of chaotic structures. Another one is the spatio-temporal chaos and vacuum fluctuations of quantized fields. Just to mention 2 very diverse topics. I would like to mention also, amongst his many papers, one recent PRL on dark matter effect of a resonance signal on Josephson junction. I like this one because it's about a proposal to measure whether dark matter is actually can be observed in the experiments in the universe. Okay, that's I think a very interesting proposal. He's probably most well known for his work on superstatistics and its applications to turbulence and the thermodynamics of chaotic systems. And recently, he has applied this concept of superstatistics to power grid frequency fluctuations in a Nature Energy paper, which is receiving much attention. He has got an IFISC, that's a ministerial grant, which deals with the stochastic modeling aspect of demand and supply in electricity networks. The title is Nash Equilibria for Load Balancing Network Power Systems with Vito Latora. Today, we tell us about this application of superstatistics to frequency fluctuation power grids.
Okay. Yeah, thank you very much, Raul, for this very kind introduction, and thank you for the invitation to IFISC, which is a fantastic institute, cross-disciplinary, and it's a great pleasure to be here for the 2nd time now. And so I also enjoyed very much the discussions this morning that really shows how friendly people are here and how you can interact immediately and talk about interdisciplinary research. So that was really nice. So as said today, I don't want to talk about dark matter, although that's also an interesting topic, but about things back to the Earth, really power grid statistical fluctuations in frequency. And so here's the concept of my talk. I first want to introduce you to the superstatistics concept, something that I invented together with Eddie Cohen, and it's quite generally applicable. So perhaps the first 20 minutes will be pretty general so that you can see that it's a useful concept where you can have a good description of a variety of complex systems using these techniques. It's actually a technique that is related to considering, in addition to the normal statistical mechanics, statistical distribution of parameters in your system, like inverse temperature, for example, that is normally not considered in an equilibrium situation, but that is very useful to consider. And then after the theoretical introduction, I show you two examples, turbulent flows and measured cosmic ray momentum statistics, where it works quite well and is quite useful. And then I come to the main topic of this talk, the main application of the superstatistics, namely this recent work on power grids. And if time remains, I will talk about a few more advanced topics like transitions from one superstatistics to another, or how to control these types of systems, and so on. Right. So that is the outline of the talk, and I try to stay elementary and basic, so I don't want to impress you with lots of formulas or so, but just let me explain what is superstatistics. Let's just consider a very simple example, a spatially inhomogeneous environment, right? So this is a region, a spatial region here, and you may have in a non-equilibrium situation a temperature beta 1 to the minus 1 here, so beta is inverse temperature, and then you can go to another spatial region with a different temperature, so it's a driven non-equilibrium situation. And if you then look at a Brownian particle that moves in this inhomogeneous environment, then for a while this Brownian particle sees this environment, but then it moves on to the other region where it sees a different temperature, and so on. And what the experimentalists are then ultimately measuring is a mixture of all these different statistics for the different temperatures, right? So that is pretty obvious. So locally, if you're long enough in this region with a given temperature there, then you see there ordinary Gaussian stochastic process, Ornstein-Uhlenbeck process for the velocity. So, but superimposed to this in the long term is also the statistics of the different temperatures, and that is relevant because you know the diffusion constant of that particle is related to the temperature via that relation, right? So you have different diffusion constants in the sake of time. But that picture is very general. You can think of this as either being spatial inhomogeneities, you can think of it of something that changes in time, that the diffusion constant is time dependent. You can think of it even in a Bayesian way, that you don't know precisely what the temperature is, and so on. So there are many versions of this concept, but what is then quite interesting and not so well known is that already this inhomogeneity generates, for example, power laws rather than exponential behavior. So that was about the state 17 years ago. We put a local Lagrangian equation into these cells, describing just the velocity of your Brownian particle which is damped there and driven by Gaussian white noise with a certain strength sigma. And then, of course, you know from Einstein's theory that the temperature is related to the constants gamma and sigma by gamma over 2 sigma squared. The beta is the inverse temperature. And now, if you assume, as a very simple example, a chi-square distribution of temperatures or of inverse temperatures in the various cells, that is this particular probability density here. It's the gamma distribution or chi-square distribution for integer n. That distribution describing the inhomogeneities is very common, right? If you take n Gaussian random variables xi and square them and add them up, then you get a random variable that is chi-square distributed with degree n. So it's something very common if you have some parameter that should be positive, so therefore you square here and take a sum of n degrees of freedom of Gaussian random variables xi, then you get this probability density for the beta. And if you now just do this simple example, given a fixed temperature, the velocity of that particle is Gaussian distributed, right, with that inverse temperature beta. The joint probability, you take the product of f of beta and p of v given the beta, but the marginal probability density, that is what the experimentalist really measures, is given by this integral over all the different betas that this Brownian particle sees during its travel. And now plug in these formulas and you end up with this. This integral gives a p of v given by this formula, which is often called a Q Gaussian in the literature, right? So you see, if you go to large velocities v, then you can neglect this 1 here, and therefore it decays with the power law, this distribution, v to the 2 over q minus 1 in the denominator here. So that means simply from the fact that we look at an ensemble of different inverse temperatures, you get power laws in the marginal distribution that is then being measured. And these power laws have this specific form. They are called Q Gaussians, or if you do plasma physics, a lot of people call them kappa distributions, with kappa equals to 1 over q minus 1. And so that was just one example, but this example can be done much more general, and that's the idea of superstatistics. So the beta need not to be really a physical temperature. It can be a general parameter in your favorite system, which you're just studying right now, and you can make your system superstatistical by making that parameter be distributed as well. Right? So I talked to this with Eddie Cohen in my office in 2002 to 2003, and I explained to him that there were new measurements of turbulent data and that they are well fitted by these Q exponentials. And he said, oh, this is like superstatistics, right? So it was really his word in my office, and so we called that joint paper then that came out of our discussion Superstatistics, and that name has then diffused around in the preprint service. It does not mean that it is a superior statistics or anything. It's just a superposition of many statistics, right? Of the one of beta and of the ordinary statistical mechanics. And in fact, you can do this for general probability densities f of beta, need not to be the chi-square distribution. You can do it for general Hamiltonians. It need not to be just the kinetic energy of a single particle. It can be any Hamiltonian for which you do statistical mechanics. So Eddie Cohen, you know probably from things like Cohen-Galavotti fluctuation theorems and many other things. So he died at the age of 94 last September, and he has always been a close friend, and we had many useful discussions on this. Now, in fact, what makes it nice is that this is a general problem that occurs in so many systems, in biology, in finance, in networks. You have some parameters that may fluctuate that you normally keep constant. And the question is, what happens then? And, so, of course, for the example of the Brownian particle that I described, you need sufficient timescale separation. Imagine your Brownian particle does not stay long enough in one cell which has more or less a constant temperature, then it doesn't have enough time to find the Gaussian distribution corresponding to that temperature, right? So there needs to be timescale separation in your system that locally after a given time you have approached the local Gaussian and then it changes to a different region where there's another Gaussian. So this timescale separation is really necessary for this to work as a good approximation. But if that is the case, then more or less your Boltzmann factors, the e to the minus beta e, are then effectively deformed in your non-equilibrium system with the temperature distributions. And the conditional probability, the marginal probability, is then you can translate it in a kind of generalized Boltzmann factor where you take the ordinary one but do additional ensemble over all these different betas in your system. And that is then the basic idea. And the nice thing is that many results of this can then be proved for general f of beta. You don't need to have the particular chi-square distribution. Many things can be proved quite generally in this case. So this is what was done then. With Eddy, we proved a fluctuation theorem in this generalized sense. With Hugo Touchet, who was a postdoc of mine at the time, we proved some variational principles for the large energy statistics of these superstatistics. Of course, all this is also related to Thales distributions. You can construct more general entropies that if you formally maximize them, they produce Q Gaussians or other types of more general distributions. But perhaps the nice thing here is you don't really need these entropies as first principle, but they come out as an effective description of just fluctuations of temperature. And so people applied that also to high energy physics, to scattering data, to random matrix theory, to one interesting thing which is already in the paper with Eddie Cohn there in 2003 is that the Q parameter is a very good approximation given by this simple formula. So you see if the beta is constant, then the second moment is the same as the first moment. This would be 1. This would be ordinary statistical mechanics. But due to this temperature fluctuation, you get a slight deformation of that. And, now, from a more practical point of view, people applied it to classical and quantum turbulence. I had just this morning a good discussion with Luisa and others on quantum turbulence. So they applied it there. They applied it to environmental data, to finance economics. That is, volatility fluctuations in finance have been for a long time dealt with, and so that is well known there. But perhaps if you want to apply it, it's perhaps good to look in the most recent papers where I want to recommend 3 of them. One is here by the group of Ralph Metzler, who really looks very carefully in this PRX how good this superstatistics approximation is for a given stochastic differential equation, and he's very much interested in applying it to complex biomolecules which have different diffusion constants. Then there's a very recent Nature communication by a group by Simark et al. Just appeared a few weeks ago, who do this very carefully, the superstatistics from a Bayesian model selection point of view. And what I want to talk about here is a more practically minded application to power grids. And since Dania, Gomila, and Beck, they are the experts on power grids here, so we had also a wonderful discussion this morning about this. But before I come to these power grids, there's one thing that I should still explain to you. The f of beta, this distribution of the beta, can be in principle anything. That depends on your complex system that you're interested in. But now after, let's say, 17 years of superstatistics, it turns out that most experimental data generated by complex systems, if they are kind of superstatistical, then you have typically three different types of superstatistics, namely either the f of beta is a chi-square distribution, that was the case that I showed you just a minute ago, or it can be the inverse chi-square distribution that occurs also quite often, and it can be a log normal distribution. And that I want to explain in just a few seconds. So this is the chi-square distribution of beta. Why is that a generically very often occurring distribution in complex systems? It's simply because of this fact. You have n degrees of freedom that perhaps determine in some way or another the dynamics of your parameter that fluctuates. And if you assume it's a positive parameter, then you have here Gaussian random variables locally. Due to the ordinary central limit theorem, many things become Gaussian, right? But the parameter is then a positive thing, so you need to square the Gaussians. And if you have n independent Gaussian random variables, they quite naturally generate this distribution. So that is something that occurs very often. But you see also, why should it be the inverse temperature that is the sum of the random variables? It could also be the temperature itself in your system. And that is the other case of inverse chi-square superstatistics. If you assume that the temperature beta to the -1 is such a sum of Gaussian random variables squared, then you get a different distribution, f of beta, which is this so-called inverse chi-square distribution. That occurs also quite often, and you may first think, oh, isn't it more or less the same whether I have that or that distribution? But it is not. Namely, if you take now the integral over this distribution with your ordinary Boltzmann factor, you don't get the Q exponentials that I mentioned before, but you get these distributions, e to some constant times square root of e. So if E is kinetic energy, if it's a half mv squared or something like that, these are exponential distributions in velocity, in absolute value of velocity. So it's different. But you see those as well. And you can slightly generalize that and then get also stretched exponential distributions from this approach. And finally, if you have a cascading process, like in turbulence, the Richardson cascade, or so, you very often have multiplicative cascade processes like that. And from those, you can easily derive that in these types of systems, it's quite natural to have yet another distribution, f of beta, the log normal distribution, which is down here. And these three distributions are very often seen in complex systems. I don't say that there aren't others, but the generic case is very often restricted to these three types of f of betas and three types of superstatistics. Now it's time for applications. So the first application was really application to Lagrangian turbulence. And again, that is a good topic to talk about here, because I know many people here look at Lagrangian tracer particles in oceans and things like that. So you really follow the dynamics of a single particle embedded in a turbulent flow. And about 17 years ago, there were very new measurements of Bodenschatz, who was in, he later went to Göttingen, but at that time I think he was in Cornell, right, in Cornell he was. And he put a particle into a turbulent flow and had excellent measurements of the acceleration of the single particle in the turbulent flow. And what he observed, what was at that time quite amazing, namely when you do a histogram of these accelerations of the particle, of just of a single component of the acceleration of this particle in a fully developed turbulent flow, then it was these data that he got. Here's the acceleration in units of the standard deviations. So these are extremely rare events, 20 standard deviations, 40 standard deviations, 60 standard deviations. And here's the probability to see that acceleration of that particle given by a histogram of these data and in a logarithmic plot. And you see it is not at all a Gaussian. In a logarithmic plot, a Gaussian would be a parabola, but it has heavy, heavy tails here. And so the acceleration is measured as small increments in the velocity of the particle. And now what you see here as the solid line, which fits the data perfectly, is precisely this formula here. And look at it, it is basically a superstatistics, namely here you have something that you could regard as a kind of Boltzmann factor, of course an effective Boltzmann factor, because here it's really the velocity difference that counts the acceleration squared. And then you have a parameter, a variance parameter beta here, and that variance parameter beta is distributed according to a log normal distribution. You integrate that up and you get quite a perfect fit of the data. And that makes sense if you look at these measurements. Then in a turbulent flow you have for a while that the particle moves in a very calm region, so there would be little variance in the fluctuations of the environment. But then it goes to a region where there's a lot of turbulence, and then the variance there is much bigger. And with these long-term measurements, you probe then many of these situations and integrate them all up like that. And then you get these distributions. So it's pretty natural. And in fact, you can then, once you have a stochastic local model for that, you can do some calculations and also reproduce correlation functions of the particle accelerations that he measured, or you can reproduce scaling exponents and things like that. So this is one example where it worked pretty well to understand the data. Now I show you a much more recent example. I like that example as well because it's on cosmic ray momentum statistics, right? So the Earth is constantly bombarded by cosmic ray particles, right? And most of them are protons, but there are also electrons and all kinds of particles. And the Earth atmosphere modifies these particles and momentum statistics. That's why they put a spectrometer on the International Space Station. And that measures now the primary cosmic rays, how they arrive before they hit the Earth's atmosphere. And there's a new spectrometer there, the alpha spectrometer, AMS2 collaboration. And they have now in the past 2 years extremely new data on the spectrum of the momentum spectrum of various particle species. So they can really decide with the spectrometer, is it electrons that we are looking at, or is it protons, or is it something else? And this is a recent scientific report where we looked at these spectra. These are electrons and positrons, and these are the data from the space station. Here, the red one for positrons and the black one for electrons. And now there are many modeling approaches to understand these spectra. But what was quite surprising to us was that you can understand them in a pretty basic way as, again, a superposition of many scattering events that take place at different temperatures. If you take the original process that produces these particles, namely two colliding protons, as you have it at CERN or so, then you have a theory called the Hagedorn theory that describes these scattering processes in a Hagedorn fireball. And now, if you assume that in this scattering process, the temperature fluctuates and is distributed with the chi-square distribution, which is the most natural thing to assume, then you can derive the spectra, the shape of the spectra, pretty basically. There are a few more tricks there that you have to use. You need to look at QCD at smaller scales to understand what you should choose for Q here. And there's also a subtlety based on so-called escort formalism. If you're an expert on that, it will say something to you that tells you that you have two different values of Q that need to be combined. Anyway, after a longish calculation, you end up with this prediction of the spectrum, and that fits the data very well. These are these green and blue lines. I should say here that we cannot predict. Here's the flux of cosmic rays with a given energy. We cannot predict the absolute rate of the flux. That requires a lot of knowledge about the interstellar medium and so on. But the shape as a function of the energy, that seems to come out quite precisely from simply superimposing these scattering events. Namely, what the spectrometer measures is really coming from so many different scattering events, which all have locally a different Hagedorn temperature. Okay, so after this excursion to cosmic rays, it's time to really go to electrons that we have here on the Earth in our power grids, right? So this is back to the Earth now, and that is the rest of my talk. Yes, I have still about 25 minutes. Good. So, first of all, the question is, why am I suddenly working on power grids here? And the reason is a very practical one. As a researcher, you need to get research grants. Now, in the UK, it is very hard to get a research grant, except if you jump onto the energy theme, because the government wants to understand the future power grid. So you have a much better chance getting a big research grant in the UK if you start thinking about fluctuations in power grids. And so Vito Latore, which many of you know, and myself, we decided we'd give it a try, and we applied for a big grant and got it 2 years ago. And that was indeed then a very good starting point. Now, the reason why the government is so interested in power grids is that they promised to reduce the CO2 production, right? And we all know that is a very useful thing to do. And but if you now look at the sources of CO2 emission in the Paris Agreement, there was some agreement to reduce this. But you see, the main half of the CO2 that is being produced is due to electricity and heat. And you may ask, oh, electricity is very clean, but it is really the power stations that produce the electricity that produce the CO2, right? So if you want to reduce CO2 emissions, you have to look at more intelligent solutions for the power grid than having conventional types of power stations. So therefore, this is the state of the grid in 2000. You have a big power plant, and you go to the various nodes here in the network and distribute that power. But in 2050, it will look more like this one. You have much smaller conventional power stations, and you have much more wind energy, much more solar energy, much more renewables, and you have distributed sources. But that is a problem that is not so much understood, how this is really going to work, and therefore a lot of research is still needed to understand that. Okay, so here is what really would be the ideal future power grid. You have lots of offshore wind turbines here. You still have some small conventional types of power stations. You have then here you have lots of solar panels locally on houses. There's some wind turbines there. You have lots of electric cars, which can be very useful in the sense that they also can serve as a battery, right? If there's a lot of power in the grid, they can store it and charge up their batteries, and then you still have the ordinary types of houses with no solar panels or so. And the question is, how is all this going to work? Do we need really this guy in the middle who is controlling everything? That is the way it is done right now, or could we dream of a net where many things are automatically regulated? So for that you need a suitable observable to understand this status of your power grid, and that is a very good observable for that is the frequency deviation from 50 Hertz. And I'll come to that back in a minute, because the ultimate aim would be, if you have a smaller grid like that, which is very clean and environmentally friendly, many things could perhaps be done automatically to stabilize the system, which is necessary because all these inputs are now much more randomly fluctuating. The wind is fluctuating, the solar radiation is fluctuating. The people, of course, they are also having fluctuating demands. They sometimes use much more energy than at other times, and how to get all this combined is a difficult question. Now, why is the frequency deviation from 50 Hertz a very interesting variable to look at? So if you have a conventional power turbine, then it is a generator like that. It rotates with this 50 Hertz, basically, right? And there are many models you can use to understand in a simple model these power grids. One of the most well-known equations, but very simple model still, is this one, the swing equation, where the change of the double dot of the angle variable, which is the theta dot, on average it goes with 50 Hertz, and then you have fluctuations of around these 50 Hertz. That obeys this type of equation. You have here the mechanical input at node I. The nodes are now, let's say, big power stations or smaller ones, and you have a grid damping constant like that, which is this term here, and then you have interactions between the nodes in your power grid with a coupling matrix Kij, which depends on the network structure and transmission properties. And ultimately, what you're interested in is that all these angle variables rotate in the same synchronous way, which is pretty easy to achieve for conventional power grids, but if there are more renewables in the future, it is not so clear at all that the thing is going to work in a reliable way because you have much less inertia in the system in the future power grid. Now, an interesting observable to look at is the frequency deviation from 50 Hertz for the simple reason if the frequency drops a tiny little bit below the 50 Hertz, then this has the meaning that there's a lot of demand in the system. The turbines work hard to meet the power demand. You need, in principle, more power. And if the frequency is a bit higher than 50 Hertz, that can be translated, there's lots of power in the system, surplus of power, you want to get rid of power. And in fact, electricity prices can sometimes be even negative because the national grid is then happy to get rid of some power, right? So simply to stabilize the system. And so this is a very, very good observable to look at, which takes into account everything, demand fluctuations, trading, and so on. And why is that so? You can think of it like a car. You're going with a car uphill. You want to achieve constant speed, constant rotation of the wheels. But if you go uphill, it will go a little bit slower, right? The frequency drops a little bit. Whereas if you go downhill, the frequency of your wheel rotating will increase a bit because you have more power available. And that is reflected in this pattern of the frequency. But that means you have there an excellent observable which you can use to perhaps design a good control mechanism and other things, right? So for that reason, we decided to model building is one thing, but what is really being seen in the grid is another thing. And so we decided to have a very careful investigation of the statistical properties of these frequency fluctuations as a function of time. And this is a typical time series that you see here. So this is 24 hours. Here's the frequency mean of 50 Hertz. This is data for the Central European net. And you see, as expected, on average, it's 50 Hertz, but it fluctuates a tiny little bit around it. And what you see here with the different colors and so on is that we repeated these measurements over a full year. So it's actually 365 trajectories. And you see how, on average, they are all here, but sometimes you have these large peaks here, and sometimes large peaks there, right? And now, if you do that on a smaller time scale of 1 hour, so these are real data, then you see every 15 minutes something happens. There seems to be like a jump in the frequency or so, and that is due to trading. The electricity as a spot market, so every 15 minutes, or in other countries, every 30 minutes, new offers are being accepted for power to be fed into the system, and that shows here, right? And in addition, of course, you see also that the variance also fluctuates. For example, here in this time region, if you see, this is much more spread out, right? Whereas here you have a smaller variance, and that cries really for a superstatistical description. In various time intervals, you have stochastic behavior with different variance. That is just the old idea of superstatistics. So therefore, it's natural then to look at a histogram of these data, right? How often you have a certain frequency deviation, and that you can do for the various European and North American and Japanese power grids. And here's an example for the Central European grid. Here's the 50 Hertz, and you see this is a PDF of having a certain deviation from the 50 Hertz. And if it were a Gaussian process, it would be this orange line here, but apparently it is not Gaussian. There are, again, some tails here. Now, there, of course, if it's non-Gaussian, you can ask, well, what is it then? And there are many non-Gaussian models. For example, you can choose stable distributions, alpha stable distributions, or generalized limit theorems for them. They lead to Levy stable distributions. That would be the best fit that we could get with that one is this green line. And you see, okay, it has tails, but it's too high here, right? Whereas the Q-Gaussian, that is based on the assumption of variance fluctuations with essentially a chi-square distribution, that gives this blue line, which is in very good agreement with the data, and Q is roughly 1.2 there for these data. So, therefore, this seems to be working again, right? Here's just a short reminder. We did that in the first slide. If you have an ordinary Boltzmann factor and fold it with a distribution of different variances, you get, for the chi-square distribution, this particular distribution, a Q exponential. That was just the Q Gaussian that I fitted to, or that we fitted to the data in the previous slide. And the energy in statistical mechanics would, in this case, simply be a quadratic function of the fluctuation in the frequency, right? So it is what was fitted there. And now you can go then further. Our ultimate dream is to have a fantastic model of frequency fluctuations which takes into account as a synthetic model all the influences for the frequency. I talked to that with Beck and Daniel Gomila this morning, and they have already a nice model, but I think it still needs to be generalized. And so the fantastic model would incorporate the noise characteristic due to fluctuating demand of people, due to renewables, due to everything. And then we can really talk about extrapolating that model to the future power grid when we understand all the influences of trading, of everything on the nodes in detail. So there's still a long path to that way. But as a first step, at least, we can say the simplest model you can think of is just the great fluctuation is damped with some effective damping and driven by some noise from various sources, and the variance of that noise fluctuates, or the effective damping constant fluctuates depending on what you prefer. And but one needs more statistics and more refined models, and then it turns out that all power grids are really different. Although the Q Gaussian is a pretty good fit to almost every power grid, if you look at the correlation function of the frequency fluctuation, it looks very different for the different power grids. So the one of Central Europe, including Germany and France, is this red line that corresponds to the Q Gaussian that you just saw. But then if you live in Mallorca, for example, then you have more this correlation function here, this blue one. Or if you live in North America, that is this yellow one. And if you live in the Nordic countries, the correlation function decays much slower here. So apparently there's no hope to have the universal theory of all power grids, but they're all different. But you need to understand these differences and in the correlation function as a function of the time scale. Okay, and here's this decay of rate of correlations. The mean is this narrow white line here. So in the Nordic countries, you have, due to this funny shape of the correlation function, a much bigger error there in the data. And but otherwise, it's pretty much centered around this 0.003 or for the various countries. for the various power grids. Now, why are there these differences? Well, because every power grid has different control mechanism, and it also has a different feed-in of renewable energy or conventional type of turbulence and so on. What I'm showing you here is such a portfolio of this power mix, but it's not the current one, where renewables are about 20%, in the UK at least, but it's the future projected one if the politicians stick to their word and reduce CO2 by a huge amount, by 95%, as compared to the 1990 situation. And if that is done, then this group here in this new archive paper made a very interesting simulation, namely to see what is then the optimum power mix, how much renewables under this condition of constraint to reduce it to what has been agreed, what is then the optimum power grid mixture for the various European countries. And that is the result. You see here the bluish onshore wind and offshore wind is by far in the year 2050 then the most cost-effective situation. There's still a little bit of ordinary gas turbines, the red stuff here. There's also a bit of battery storage and hydro reservoirs and so on, but most of it is wind, except in countries like Spain, where solar energy, or Italy, where that would have a big impact. And so this is a projection, and it turns out in this interesting paper that then it is also very useful to cooperate. It's so the opposite of Brexit. There should be big transition lines from the various countries where they exchange their energy, and that makes completely sense as well. Namely, if there's a lot of wind in the UK and no wind in France, then it makes perfectly sense to transmit the power from the renewables down to France and other way. So that is the cost optimum solution in this interesting paper. But if that is the case, if the future power grid is really so much cost optimized, containing so many wind turbines, then there's a big question: is the whole thing still going to work in a stable, reliable way? Namely, if you look here what solar and wind are producing, the power from a wind turbine, this is the power, and this is how often that power change is seen. What is plotted here is actually the increment statistics. So it's the difference of power emitted by a wind turbine on a scale of 1 second, of 10 seconds, and 1,000 seconds. Again, in a logarithmic plot. And what you see here is, again, this is not a parabola. The green stuff would be a Gaussian distribution of these wind power increments. It is not at all Gaussian. It has heavy tails, as we would expect, again, from also from a superstatistical point of view. It's clear the wind sometimes blows strongly, and then there are much calmer periods. So you have heavy tails in the wind increment statistics and also in the original statistics, but less pronounced. What you see here is actually something that is not only in that paper but also in earlier paper. People had looked at wind velocity fluctuations and have seen that these obey often inverse chi-square superstatistics, which is generating effective distributions which decay as an exponential of the absolute value of the wind velocity. You see that here, this is in pretty good approximation, a straight line in this logarithmic plot. So you do have a very complicated power tail statistics of wind energy. For solar, it's even more complicated, and So now imagine you have these strongly non-Gaussian noise sources in your power grid as main ingredients of the power grid. Does it really work? Are we sure about that? And so I think at least one needs to do a lot of research on it, and one should design appropriate control mechanism, which can be ideally used by looking at the frequency observable as a good observable, and that work is done here at IFISC by Per and Dania. But there are many control methods, not one, but one should think about it to stabilize the system, and that is really useful to know. Okay, yeah, here you see again another thing we had in the Nature Energy paper. You would naively think if there's more renewable energy generation, then the effective noise strength of this complicated stochastic process increases because renewables like wind are fluctuating, and roughly we see that in the data. So in the UK, where we have a high proportion of wind energy, the noise strength, the variance is pretty high on average, whereas in Mallorca, I think you're in a very interesting island here, because fluctuation-wise in frequency, it's pretty small and isolated, right? So it's an ideal test ground, and Mallorca on its own, I think, has no wind energy contributing. And therefore, it is here at pretty small in the effective noise strength. Okay. Now, last thing with Harry-Sweeney, we had a general method. How do you get this distribution f of beta that underlies the superstatistical approach given a measured time series? That is a very natural question. And there's a nice algorithm. Basically, it exploits the fact that you have a succession of a Gaussian stochastic process with that variance, then a bit later with a bigger variance, then again the variance is different. So you want to find the optimum time slicing to find the distribution of these variances, and that is done by this algorithm, which I don't have to describe in detail here. You can look it up in this paper with Eddie Cohn and Harry-Sweeney, where we applied it to turbulent data, but you can do the same for the power grid, and for the power grid you then get something like that the kurtosis matches 0.3 here, so that means locally you have Gaussian behavior on that time scale, but with fluctuating variance, and once you have that time scale you can do a histogram of the variance parameter in these time slices, and that is the result then for the example of the Japanese power grid. So you have a distribution in these frequency fluctuations of the effective variance parameter or the effective damping, whatever you want to call it. And for the Japanese power grid, we extracted this here, which is very nicely fitted by a log normal distribution in that case. But for other power grids, it looks slightly different, and it is a good characterization of the individual power grids, and so we should try to learn which effects. Is it mainly people? Is it mainly renewables? Is it mainly solar or other fluctuations that influence it, that explain these different types of distributions? Okay, I come to the summary. It's 4 o'clock. I hope, no, this is not the summary. Some advanced topics I don't have time to talk about it. We did superstatistics in a bit more sophisticated ways, for example, with several variables. And we also asked, similar as here in Mallorca, how to control the power grid. So this is some papers if you want to get more into details onto these topics. So here's the summary. I hope to have explained that it is something pretty general, which you can ask for many complex systems. Is there a distribution of a parameter that you would normally assume to be constant in your system? And if yes, what is that distribution, and does it influence your system strongly. And then you could check whether it is perhaps one of these three universality classes that very often occur in complex systems. So either the chi-square distribution or the inverse chi-square distribution or the log normal distribution. I showed you some examples where this seems to work quite well. There are other examples I hadn't time to talk about, but if you read the papers of Metzner in PRX or so, he's mainly interested in complex biomolecules which diffuse with different diffusion constant, and there from the different diffusion constant comes this ensemble of superstatistics there. And for the power grids, it is really, it is a first order understanding why the distribution is non-Gaussian at all, right? It's very natural to assume that the conditions change in the power grid all the time. And so we extracted it for many different European power grids, have good data, but need more data actually. And so probably more measurements will be done in the future, and maybe even one could produce a database of all these nice frequency data. That would be a very good thing to do. And what is really influencing all these fluctuations in the power grid is indeed a very complex system. It is engineering, it is turbulence in the renewables, it's people with their different demand pattern, it's economics because you trade power. So it's basically everything that feeds into this single observable of the frequency deviation. And it's really very worthwhile to study that, a very good thing to do. So I end this talk with showing you pictures of some of the people who I collaborated with and about which work I talked to you. Okay, thank you very much.
Any questions?
So you said to get superstatistics, you got this superposition of many stochastic processes with Gaussian distribution,
Yeah.
and then you have that if the variance of each one is
Yeah.
varied, you get superstatistics.
Yeah.
And how is this variance? So how is the so how much the variance change? Can be anything. So for instance, if it is something sinusoidal, that's already give.
Oh no, yeah. No, in principle it can be anything, but what we see in practice is these three distributions, right? You can now ask what causes, for example, the log normal distribution. Then you could put in an additional cascade-like multiplicative model that produces a log normal distribution in the variance. But for the chi-square superstatistics, you could produce a model that has a chi-square distribution again from a microscopic dynamics. For the sinusoidal that you mentioned, you could do that, but it is, in practice, I don't think there are many systems where you have periodic...
that would give you also superstatistics?
Yeah, it would give a superstatistics, but one that would not... probably have different characteristics. But there's an interesting thing. If this distribution f of beta that you get, if that is sharply peaked, then it does not depend on details of this distribution, whether it's log normal or chi-square or inverse chi-square. But in leading order for a sharply peaked distribution, you always get something that is pretty well described by Q Gaussian. So it is... in a sense, it's universal. In another sense, it's not universal. So different systems may create different superstatistics. Yeah. Oh, sorry.
Yes. So, well, general question connected to the previous one. I mean, you discuss many systems, right? Where this superstatistics can be applied. Are there systems where superstatistics can be?
Whether it cannot be. Yes, of course, there are many systems. Yeah, the limitations are pretty clear. You see, suppose you have a Q Gaussian distribution, right? You could have a different stochastic process. One that is constantly producing a signal that all the time, on every time scale, has this Q-Gaussian distribution for some reason. But the superstatistics is something different. It says that it is the usual Gaussian, but then with a fluctuating variance, and then the variance changes again. So you're given a time series, you could do a test, and that is also in the paper with Harry Sweeney, defining a test parameter. Is superstatistics a good model for the time series or not, right? And there are certainly many, many systems that are not superstatistical, where the variance is perfectly constant and the distribution is Q-Gaussian on every time difference you look at it. And so therefore it's an interesting question. I mean, some systems are like that, but others have nothing to do with superstatistics, because you need this separation of timescales in particular, right? You need to give the system time to reach a local equilibrium before it changes to the next state.
On this topic of general superstatistics, I was wondering if people have also looked at the situation where on the short time scale you have a multiplicative stochastic process,
Yeah.
but with parameters that are changing.
Yeah.
So for example, suppose that you have avalanche dynamics,
Mm-hmm.
then the random variable does excursions rather than Brownian motion. So
Yeah.
the probability distributions for those excursions are actually chi-distributed. This
Yeah.
will suppose then the variance is also chi-distributed. So you
Yeah.
have this hierarchy. So
Yeah.
to which extent this model can be generalized to even more complex?
Well, I think that is in this one, what I measured here. If you look into this paper, which I have with a group in Prague, we look there at several superstatistics which are intermingled, right? So you could do a lot of things there, right? And depending on time scales, maybe it's sufficient just to look at one superstatistics there, but on other time scales you need 2 or 3, and so that would be.
But what I'm reading with this story is if it's possible to apply this superstatistic concept to avalanche dynamics, stick-slip events.
Yeah.
But there, the basic process typically it's not Gaussian, but it's more like an excursion process.
Yes.
So
Yeah.
then
Oh, well.
generalize that.
Yeah, so you have then again a parameter, and you may not also that you have locally a Gaussian is not at all necessary. You could have whatever distribution which depends on a parameter, and then make superstatistics with that. But that is included here because, for example, you could do a superstatistics of Q Gaussians where the variance of the Q Gaussian fluctuates, but you can reduce it to 2 superstatistics where the first one generates the Q Gaussian and the second one then the variance of.
So I think something like this could be applied to study earthquake dynamics.
That would be very nice. Would be very happy to.
And I have another question. You presented those graphs with distribution of increments in the wind.
Yeah.
It's very much like the velocity increments in turbulence.
Yes, indeed. And indeed, the turbulence has been studied a lot. And as you know, in quantum turbulence as well, you have these very large increments. And so the power statistics of these wind turbulence clearly resembles the 2-point and endpoint statistics in turbulence. And it is not precisely the same, but very much the same origin.
When you have the distribution of the energy state, you operate over the betas.
Yes.
So everything has a ultimate equation, which is the distribution of betas.
Yeah.
Okay. Now from the mathematical point of view, you have a Laplace transform.
Yes.
You can get from the data, you can get f of beta.
Yeah.
Is there a way of, has been a case in which you can determine f of beta and then determine this is an appropriate, measure that from other beats? For example, f of beta is a chi-square.
Yeah.
You can measure directly distribution of betas in your system, not just the aggregate of the
Oh, yes, you can do that. And this is, in fact, this is for a time series where the beta is produced by time fluctuations. It is really, this is a direct measurement, because I didn't have much time to go into it, right? But you slice your time series into appropriate lengths, intervals of length t, and then within each t, you calculate the variance here, well, assuming the average is 0. The beta is then given by the variance of the signal in that time slice. And then you do the histogram of the beta, and by doing the histogram, you have a distribution of, so you measure it in a sense directly with that algorithm, and then you can check consistency whether the integrated distribution comes out with that distribution that you get from that measurement.
I think you have mentioned several times temporal correlations.
Yeah.
I don't understand how can you get temporal information from, as I understand, you are using single time statistics.
Yeah.
So can you get temporal correlations from the superstatistics approach?
From yes, you. Well, these are we just applied here. These are temporal correlations. We measured them from the experiment later, and that is what you get. Now you may, however, ask, as you asked, could I predict perhaps the shape of the correlation function using the superstatistics approach? And you can do that. I didn't show it here, but it depends then, if you assume locally a linear Lagrangian equation, it depends whether you assume that the gamma, the damping constant, fluctuates, or whether the sigma, the noise strength in your local Lagrangian equation, fluctuates. You get two different answers. So measuring the correlation function of your system can give you hints of what is really fluctuating in your system. Is it the noise strength on a large time scale, or is it the damping constant? So there are ways to calculate the correlation function. Also for the turbulence data I showed, that there are, using the time scale separation, you have a way to express the correlation function in terms of the local correlation function, in this the Ornstein-Uhlenbeck process. But yes, short answer is you can use it in a certain approximation to make predictions how the correlation function should look like. If you're interested, I have an EPL with a PhD student, Xian Mia, where we calculated various shapes of correlation functions, appeared about 2-3 years ago or so.
On a different, say, scope, some time ago there was a debate whether the fluctuations in turbulence and the ones in economical markets were similar or not.
Yes.
And there was a paper by Mantegna and Stanley in which they compare the statistical properties of the turbulence in a wind with the turbulence in the stock exchange. But they don't use this methodology.
Yeah.
They just look at power spectrums. Look at, so my question is, if this has been applied to compare these two cases, since basically this sort of processes, the superstatistics has been applied to turbulence, and since in economical systems you know that the parameters change in time, like the fluctuation, global activity changes in time, if there is an accurate comparison of superstatistics in turbulence and in economical
there is, in fact, so in turbulence one has seen that three classes are relevant in turbulence. The chi-square superstatistics, well, Louise had to leave, but in quantum turbulence, it is very well described, the velocity statistics by chi-square distribution. The classical turbulence can be distinguished from that, so it is more described by log-normal superstatistics. Now, the wind, the environmental turbulence, is best described by the inverse chi-square superstatistics. So if you already say turbulence, you first have to specify which type of turbulence. And in finance, it seems very similar. At least Yitzba in his work has seen that on on large, if you look, normally people in finance look at log returns of share prices, right? And the log returns, if you you have to specify this time scale on which you take these returns. On large time scales, it's best described by a chi-square superstatistics, whereas if you go to seconds, log returns on seconds, really micro trading by computers, it's better described by log normal superstatistics. So it depends on the scale, and but in that sense you have similar universality classes.
There are more relationships than the ones that...
yeah, there's not just one to finance one.
No, they are completely different.
No, I think there are many versions of the same topic.
Yeah, because they basically use wind, and in the economical side they use the Standard & Poor's 500, I think.
Right, yeah. No, but already within the turbulence systems you have at least three different.
There was difference in the power over distribution and difference in the conversion times. I mean, there was significant differences.
Yeah, that is to be expected, as there are different superstatistics. You wouldn't expect a universal answer for every. Yeah.
Any other questions? If not, it's time. Please come back again.
Okay.